Hello everyone, welcome to our video. Welcome to our lecture series of Structure 2, where we are going to talk about different method for solving indeterminate structures, like method of constant deformation, moment deflection method, subdivision method, etc. So in our first video, we are going to talk about method of consistent deformation. This method is also called as a force or flexibility method, and this is a general method for analysis of indeterminate structures. So firstly, let's talk about indeterminate structure. So we have an example of indeterminate structure right over here. As you can see, we have a fixed end over here. We have a fixed end right over here, and we have a roller support over here. As you can see, when we have a roller support over here, let's count the number of reactions. As you can see, we have one reaction acting in horizontal direction. As this fixed end support, we'll have moment as well, moment at A, and then we'll have a vertical reaction as well. Meanwhile, at B, we have just one single reaction acting upward. So we have a very simple formula to calculate indeterminate structures, which is R minus 3. So we're going to solving indeterminate structures by, in this video, we're going to talk about the method of consistent deformation, method of consistent deformation. So as we know, we have three reactions, three relations to solve any structures. We have x equals to y, Fy equals to z. This is force at x direction horizontal. We can take any direction as positive. Let's say this as loss is equals to 0. We can take upward reaction as positive, or we can take clockwise like this. We have three reactions, three normal equations to solve. We have three normal equations to solve any structures. So right now we had this equation of load P was acting. We had end A and we had end B. So we have three reactions: upward, horizontal, and moment at we have moment as well at end A because it's of fixed end support. Meanwhile at B we have only upward By. So we have AY acting upward AX and moment A. So we have a very simple formula to calculate whether the structure is indeterminate or not, statically indeterminate or not. We have the formula as R minus 3. If this value is greater than 0, which means it is indeterminate structure. So as we know, right now we have here 1, 2, 3, 4. So we have a very simple mathematical relation to solve any equation. Let's say if we have two unknown variables x and y, then we'll need two equations. Let's say x plus 3y equals to 0, or x plus 4y something equals to 5 something. This is just an example. In order to solve two unknown variables, we'll need two equations. We'll need two equations. So as you can see here, we have three normal equations in a structure. So in structural mechanics, so we have right now R minus 3. We have currently 1, 2, 3, 4 minus 3, which is 1 greater than 0. So this structure we have over here is statically indeterminate. This is an indeterminate structure. So we have different methods to solve the indeterminate structure, which we will be discussing in our this lecture series of this lecture series. So do subscribe the video and do follow us in order to get notified with our videos. So let's move on to our example. So firstly, what we'll be talking in our video will be talking about method of consistent deformation. So method of consistent in order to solve any equations by method of constant deformation, what we need to do first of all is we need to remove that redundant reaction. As you can see, we can remove any redundant reaction. We can remove RA. We can remove. We have AX. We have AY, and we have BY, and we have M. So what we'll be doing is we'll be removing BY because it will make our work easier. So whenever we remove this extra slash is also called as a redundant extra or redundant reaction. The structure will be determinate. So as I mentioned before, we have three equations. So right now we have four reactions. So this is indeterminate by degree of one. So just if we remove one reaction, our our beam or our whatever we're dealing with. It can be with frame also, it will be determinant. So right now we have removed this reaction by. As you can see simply over here, if we remove this support by, our beam will get deflected. Over here. So hopefully you all are clear till here. So if I remove this extra support, what will happen is my beam will get deflected in this way. So deflection at point A will be zero because at point A will be zero because it is a fixed end support, and the deflection will go on increasing in this way. So hopefully we can take this with a simple example. If I have a beam over here and if it is not supported at the other end, if I put a load, it will still be deflected in this way. You can see this is our deflection from our original. So this is our original position. It will get deflected in this way, and this deflection is denoted over here as del V is noted as del B. So in order to solve for this, so I have written some points over here as well. This method involves removing enough strains from the indeterminate structure for render it to be statically determined. So let's say if we had, let's say, five reactions or six reactions in our beam, six reactions. So in order to determine it, we have three questions. So for five, we need to remove two supports, and for six, we had to remove three supports. This will be much more clearer when we'll be moving into our examples. So firstly, in our condition, we have deflection at B is denoted as del B, and we'll denote this as del B equals to 0. And we have for del B equals to 0 as del B naught plus FBB dot By equals to 0. So now we'll be talking about all this term. So now I'll explain you about what all these terms are. Del B naught plus FBB dot By equals to what? So basically, so I have written over here del B. Del B is our deflection, which is caused when we remove the support, while FBB dot By. Okay, so FBB. So I'll explain this in the later part of the video. So let me talk a little bit more about our constant deformation. This determinate structure, which must be stable, is referred as a primary structure. So there is a term as primary structure. Okay, let me explain in the figure below. And the excess restraints removed from the given uh, okay, so I'll explain all of this in this from the figure below. The redundancies are applied as unknown nodes in the structure and their value determined by solving the comparative equation at joints. Okay. Uh, so firstly we have our actual beam over here, which is indeterminate. This is indeterminate by one. Indeterminate by because this has just only one extra support, one extra reaction, which we have removed over here. So this is our primary structure, which is mentioned here. Primary structure simply refers to the structure which is determinate structure, which is obtained by removing the extra extra reactions. Use the word reactions. This may be reaction or it may be the word reaction. So if we have extra reaction one, two, three, we'll remove all of them. We may remove one reaction, we may remove the two reaction until the structure is determinate. So first this is our primary structure. So as explained before, once I remove this redundant means extra. So we have one, two, three. So we have three to be determined determinate. Since this has four, this is indeterminate by one. So we remove this extra reaction from the point B from the point B. That extra reaction is known as the term redundant. Redundant simply refers to the meaning extra. Extra. So let me again turn this on again. Now what we do next is now we have the redundant BY. As you can see, this structure will not be stable. So as I explained before, once I remove the support from it, it will get deflected in this way because of the load B acting somewhere along the length of the grid. So what happens is we will provide a redundant reaction BY. So this By simply is the reaction. Is simply, sorry, not the reaction. Let's say we can say the reaction or the reaction force is simply the reaction force which is equivalent to that support. This is equivalent to the support. So we have redundant By acting over here, though it simply refers to that force which is able to sustain the beam from getting deflected. So this By will instead provide us an upward deflection, which is equivalent to del Bb dot By. So this is our beam under action of redundant By under action of this By simply is equivalent to our support By which we removed earlier. So let's move on to a little bit of more of example and it will be more clearer. So as I explained before, this is our structure. This is an example of our structure with a single degree of indeterminacy, which is at point C. So we remove that. Remove that extra support and we denote it as CY. This is our primary beam. A primary beam is when the beam is removed by that extra support, which is subjected to external load. External load CY is that load which will do that function of that support, extra support, in order to make the beam stable, in order to make sure that the beam is not deflected. So as you can see, del C equals to 0. Let me explain it again. I have a simple pin over here. I have a support over here, some kind of support. If I remove this hand, what will happen is due to the load acting at, the beam will get deflated. So in order to make sure that the beam is not deflated, I'll provide an extra reaction acting upward in order to make the beam stable. In order to make sure that the beam is not deflated, that extra, which I refer to as redundant force, is referred to as Cy over. This is my extra redundant force. This is my primary source subjected to external load and redundant. So this force needs to be such that deflection at C, del C needs to be 0. So let me move on again. Primary beam subjected to external load. Okay, primary subject being subjected to external load and redundant. So external load means here, external load means B. This is our external load, and redundant is CY. So in the next case scenario, what we are doing is our beam, primary beam is not subjected, is just subjected to external load. It is subjected to external load only. So as a result, since there is no any redundant CY is not acting in this case, we are not providing this. We are not providing this external redundance. What will happen is our beam will get deflected. Beam will get deflected in this way, and deflection is written as del C naught. So now moving forward, we provide that extra redundant force Cy, uh, Cy, so that the beam gets deflected upward, and we denote this now as del Cc. So we have terms like del C naught, del Cc, Cy. So let's explain this. So we need to provide that external redundant force in this way. The main principle is that deflection at C, del C. So this was our original beam A. This is our external load acting at B, and we had our support C. So we remove this support, but our main principle behind the method of constant deformation is such that deflection at C, del C needs to be 0. So del C equals to 0. Now we write this as del C naught plus del CC equals to 0. And our del CC, so this is our deflection at C due to, okay, so let me explain what is del CC. So del CC, we have our equation for, in order to find del CC equals to FCC dot CY. FCC is, so we have FCC over here. FCC, okay, so FCC is, so we have del CC is this value. Del CC is this value deflection which is upward when CY redundant is acting at point C. So FCC refers to deflection at point C of primary beam due to unit value of redundant CY. So the deflection we get at point C due to unit value of redundant, we take this as 1. Whenever we take unit value of redundant and the deflection which happens at C due to deflection due to the force acting at C, that is called as FCC, and this is also known as flexibility coefficient, and it has a unit of and it has unit of deflection per unit force. So this all the terms will be more clear when we move into our problems, problem 1, problem 2, which is our next videos. If we're not clear with this term, do check our next video. It will make much more clear regarding what are all these terms. So simply we get a equation which is In order to find that force Cy, which is equivalent to that roller support at C, what we do is we use this equation del C naught, which is deflection at this case, plus del CC, which is at deflection at this case. So overall, del C, which is deflection at C equals to 0, which is divided into two subcases of del C naught plus del CC. So we get del C naught plus del CC equals to 0. Del CC simply refers to FCC dot CY equals to 0. CY is our redundant force, which is equivalent to our extra support. So del C naught plus FCC dot CY equals to 0. So we simply get Cy equals to minus del C naught divided by FCC. So this is our formula. Formula in order to calculate our extra force. So as you can see, as I explained before, this was our initial case condition. A, there was a load P acting at B, and we had a C. So we simply remove the support by redundant force Cy acting upward, which is equivalent to minus del C naught divided by FCC. So this will be more clear when we move on to our example one. So in this case, we took force as redundant. We took our upward acting reaction as redundant. So we can take a moment as redundant as well. There are different case scenarios. In our case too, what we can do is we can take moment as a redundant. So this is our indeterminate beam. What we will do in this case is instead of taking Cy, the reaction at point C as redundant, what we can do is we can take the moment at Ma as redundant. So if we remove this Ma, what it is, let me write it over here only. We have this. Here is our point B. Here is this. See, if we remove this redundant, it will just have vertical and horizontal reaction, which is equivalent to having of hinge support. So at a roller support, we only have vertical reaction, but we have horizontal and vertical reaction. So if we remove this moment reaction, if we take moment as redundant extra, what we will have a beam with having roller and hinge support. So once that moment is removed, the beam will get deflected in this way. The beam will have some sort of deflection, and we have the deflection. We have a slope over which is denoted as theta AP. Slope at P is denoted as theta A naught. Sorry, it is denoted as theta A naught, which is the slope at A, which is obtained by which is a result of because of that removing of the moment reaction. So next we have this. We can divide this into two cases, like into two sub cases as well. One where we have removed that extra redundant moment and we get that slope theta a naught. And next, which will be the combination of, and next we'll have our primary beams of the tape redundant MA. In the previous example, we had our primary beams of the tape redundant for CY. Now since we're taking moment as redundant, in our soft case we need to provide moment as redundant. This primary is redundant MA, and this will be equal to FAA dot MA. So in this case, in the previous case, we took deflection at C equals to 0. Now we will take slope at A equals to 0. Since we are taking moment as redundant, we need to take slope at A equals to 0, which will be equal to theta A naught plus FAA dot MA equals to 0. MA will be simply equal to minus theta A naught divided by FAA. So FAA is the rotation at A due to unit redundant at A. So if we provide certain rotation at A, there will be so if we provide certain unit redundant moment at A, there will be certain rotation that is denoted as FAA. So this will be much more here when we move on to our examples. So theoretically, it's a little bit of difficult to explain. So if we're not grasping it right now, we can move on to our problem number one, two, problem number one, two, and so on in order to get a clearer view. So we can have a multiple degree of intermittency as well. So as I explained before, so let's look at this example. So we have beam which is subjected to certain UDL, and as you can see, we have one hinge support, and one, two, three, four roller support. So we have two reactions AX, AY, and we have one vertical reaction, two vertical reaction, three vertical reaction, four vertical reaction, dy, cy, dy. And so it's our indeterminate beam, and it is indeterminate beam by, so as I said before, our formula is R minus 3. So we have 1, 2, 3, 1, 2, 3, 4, 5, 6 supports, sorry, 6 support reactions. 6 minus 3 is 3. So we have R minus 3. So right now we have 6 supports, 1, 2, 3, 4, 5, 6 minus 3 is equals to 3 greater than 0. So it is indeterminate. So we need to, it is more than 0 by 3. So we need to select 3 support reaction. We need to select 3 support reaction as redundant. So we can take any three reactions, but it will be much easier if we take central three. So we have taken By, Cy, and Dy as redundant. So primary being subject to external loading. Since our external loading is this UDL, this UDL is our external loading mentions our primary beam subjected to external loading and redundant. So redundant is By, Cy, Dy. So as explained before, these supports are removed by our redundant reactions named Dy, Cy, Dy. So basically what our support was doing was it was providing us vertical reactions. So the same function will be done by By, Cy, and Dy. So we will remove them. So if we do not have those redundant forces By, Cy, Dy, after removing those supports, our beam will get deflected in this way: del B naught, del C naught, del D naught. As you can see, we have three unknowns. So in order to solve three unknowns, we need to have three equations. So this is our So basically, what we will do is we will have our primary beam sorted to external loading. So firstly, we'll just provide redundant By. So we have deflection at B is equal to deflection at B due to redundant at B. This is our dot By. This is our deflection at C due to FCB equals to deflection at C due to redundant at B. So similarly, FDB. So whenever we will have provide redundant at B, which is our By, there will be deflections caused at B as well as C and D as well. So this is our beam. If I provide a certain deflection upward, my beam will not move upward in just at this point. Our whole beam will move upward from that point onwards. So this is our case scenario. So we have FBB dot BY, FCB dot BY, FDB dot FDB dot BY. So now, further moving forward, so what we can see over here is similarly, similarly what similarly what we'll do is we'll have our primary beam loaded with unit redundant Cy and primary beam loaded with redundant Dy. So we have three. This will get a bit lengthy. So as I it will get a bit lengthy, this will be much more clear when we move on to our problem three for this case scenario. Next, what we have is next we'll see the deflections, upward deflections for our redundant Cy. So what happens is when I apply the redundant Cy, there will be a deflection upwards. Is FCC is deflection at C due to redundant at C dot Cy, and we have FBC, which is deflection at B due to redundant at C dot Cy. As you can see, this needs to be multiplied by Cy. Similarly, for Dy as well, there will be FBD dot Dy, FCD dot Dy, FD dot Dy. What we will do is we will take firstly del B equals to 0, which will be del B naught plus FBB dot By equals to FBy plus we have FBC dot Cy equals to 0 plus FBC dot Cy equals to 0, FBD dot Dy equals to 0. So what we will do is, so firstly for let me use another color for this one, use the red color. So let me just post for deflection del B equals to 0. I will just see the case scenario for B. We have three case scenario for B. Del B equals to 0, which is del B naught plus, I have to explain what is del B naught plus FBB dot By plus FBC dot Cy plus FBD dot Dy equals to 0. Similarly for C, del C naught plus fcb.by fcc.cy plus fc.dy equals to 0. And when we solve these three questions, when we'll be solving all these three questions, we will get our value of by, cy, and dy. This is our basic introduction to this is our basic introduction how we can solve our indeterminate structure by using method of constant deformation. So we have different problems. We have our problem one, problem two. We have we have a bit of formula as well in order to calculate this del B naught, del C naught. So we have our let me give a bit glance of the formulas as well. So we have our formula as del B naught equals to M naught MB divided by EIDX. So M naught refers to bending moment at any section due to external load, and MB is bending moment at any section due to unit load at B. Yeah, PB is MB square by EIDX. So this will be much more clear when I explain into our example one, which will be in our next video. So if you like our content, to subscribe the channel. If you have any queries, please comment down below. So thank you for watching.